Hi, welcome to Unit 65. In this unit, we're going to talk about the mass loss and the death of a low mass star, similar to the Sun. So, in this case, we're going to talk about how the end stages of that low mass star go through, and then what drives basically the red giant and how its atmosphere is being affected by that stage. Then we're going to talk about the planetary nebula that forms and basically expels a lot of the gas that forms the next generation stars. And we're going to describe the properties of a white dwarf and how it evolves on the HR diagram. If we look at the sun, which is a low mass star, typical of this size, okay? Its protostar stage takes about 1 million years, okay? As it's going to collapse due to the force of gravity, gravitational energy is converted into potential gravitational potential energy is converted into kinetic energy, which means higher and higher temperatures until it becomes a pre-main sequence star getting ready to basically start fusing its core. That takes about 20 million years, okay, 20 times longer than its protostar stage, okay. At that point, once the nuclear reaction starts and it ejects all of that, basically when it was in the protostar, all of that gas that was surrounding it, then it's going to go through its main sequence age. The sun will last for about 10 billion years from the day it started its nuclear processes inside its core, all the way to when it runs out of hydrogen in its core. So this is the main sequence stage, okay? 10 billion years. The sun is roughly about 4.5 billion years of its age. It's almost midway, okay? Then it's going to go through a red giant stage, which will last for about 1 billion years. So in this case, now we're fusing the hydrogen in the shell. The sun is swelling because of the less nuclear reactions at its core. So it's going to collapse further. Its temperature starts to increase until it starts fusing helium through a stable, more or less stable stage that lasts for about 100 million years. And until that runs out of in the core, so still fusing hydrogen in its upper layers. So it's going to go through basically a Myra variable where it's going to start fusing basically these elements and forming more and more. So the luminosity is going to fluctuate a little bit, and then it's going to shed all of, once it runs out of fuel basically in its core, whether helium and hydrogen, then in this case there is nothing to maintain it, so the radiation starts to become too high from the flakes of carbon that form, and that exposes the sun and the core of the sun, I should say, or the core of that low mass star. And so in this case, the gamma rays that were coming from the nuclear reactions before they become exposed, so they become super high energetic, that pushes more and more that planetary nebula, and the core itself will be exposed and its temperature starts to cool over time. So this is in a nutshell how the process works for a low mass star. Again, this is a description through the HR diagram and how the star evolves from protostar, pre-main sequence star. Now it's a main sequence star. The sun is roughly about 4.5 billion years in its main sequence star, midway in its 10 billion 10 billion years of age. So it's midway, roughly midway. So and then after that, once it runs out of hydrogen in its core, or at least doesn't fuse that anymore, it's going to go through the helium stage that lasts about 1 billion years. So total life so far it's about 11 billion years. Everything else is really a fraction. Even 100 million years is nothing compared to 11 billion years, okay? So in this case, once it runs out of helium, once it starts to do helium flashes, because it's going to burn them a little bit depending on how much hydrogen it has in its outer shells. Once it runs out of those, once it actually goes through those and starts to burn them, the temperature will be high enough for helium to start to fuse. That lasts about 100 million years. As I said before, those millions of years are nothing compared to the billions. So by this time, practically the sun is over. Its lifetime is done. But it still has some stages to go through, including this Myra variable stage, where those fluctuations basically of the hydrogen inside its core, once it runs out of that, there is nothing. I mean, the sun is not capable of fusing heavier elements, namely carbon or anything like that. So at this point, its temperature starts to, it exposes the planetary nebula is ejected. Once it's that, so the white dwarf is exposed, then that's basically its temperature will cool down from super high temperatures in here up to something around 25,000 Kelvin. Okay. So that's basically the surface temperature of the sun. So this is the relic temperature, the relic heat from when it was a star. And it's going to be emitted into the cosmos, into the universe, and that's how it loses that energy. There is no way for it to replenish it, so the sun will cool down until it goes completely, basically dark at some point. So this is another way of describing the same process, at different stages until the nebula forms and exposes. Once it runs out of materials inside its core, exposes the core as a white dwarf. Okay, this is the same thing, and here explaining it basically through a process, except in this case how the carbon flakes or silicon flakes form on its surface, and those flakes actually are driven by the stellar wind to expose the core, and those are actually high frequency photons, basically X-rays and probably even gamma rays. Okay, and that's how the planetary nebula is exposed. Sorry about that noise. If we look at the Hourglass Nebula, this is basically what we have. The planetary nebula is being ejected, and inside the center of that, there is actually the white dwarf sitting at about 25,000 Kelvin in terms of temperature. This is just basically a summary of the whole thing, okay? And protostar stage about 1 million years. Pre-main sequence stage is about 20 million years. Right now, the sun, this is not for the sun only, for the basically the star similar to the sun in size. So this is about 10 billion years, then about a billion years. So the G in here stands for a giga. Okay, so giga is 10 to the power 9, which is a billion really. Okay, so a red giant is about a billion years, and yellow giant is about 100 million years, and then the Maya variable is only about 10 million years, which is nothing. Okay, and the planetary nebula will take about 10,000 years to basically leave the core by itself, exposed, sitting at roughly about 25,000 to 30,000 Kelvin. Thank you.